In this video, I'll give some more details on using the theoretical biogas tool in OBA, the online biogas app, for predicting biogas production. So in particular, I'm going to show how we can use it to estimate biogas composition, as well as microbial biomass production and consumption or mineralization. So we're going to start by entering the composition of some hypothetical food waste, which will be based on macromolecular composition, and I've assumed it's 45% carbohydrate, 15% protein, and 40% lipid. That is in the organic fraction of this food waste. So our result right now is 660 milliliters, the maximum methane that could be produced from 1 gram of the organic matter in this substrate. In order to get more details, we can select the More Details button, but we don't get much more. But let's see if we can get biogas composition. So to do that, we need to select concentration. We need to enter concentration. Let's assume we have 80 grams of this organic matter per liter. And we need to specify substrate degradability. Let's assume it's relatively highly degradable. We'll set it at 85%. So that means 15% is not degraded by the microbial community. But additionally, we cannot assume that 85% then goes to methane and CO2, because some of what is degraded is going to be used for cell synthesis. So let's set that at 10%. And we need to provide two more pieces of information here. We need a reactor pH and a reactor temperature in order to predict CO2 partitioning that'll let us estimate biogas composition. So let's say this is running at a pH of 7.9 and a temperature of 55. So now what do we have? Let's go through all the results. We have a chemical formula, which is based on a generic formula for each one of these macromolecular categories. We have a standardized volume of methane of about 41 liters per liter of our feed. The overall microbial reaction results in 62% methane, but that's not what we see in the biogas. What we see in the biogas would be around 68% methane, and that's based on a pH of 7.9 and temperature of 55. So what's in the biogas has more methane because some of the CO2 that's produced remains in solution. We're looking at microbial biomass production of around 9 grams per liter and some mineralization of nitrogen. So that would be production of ammonia equal to about 130 milligrams of nitrogen per liter. And we also have estimates of the CO2 volume produced and, of course, total biogas volume produced. All the volumes here are standardized to 1 atmosphere of pressure, dry conditions, and 0 degrees Celsius. And where this tool can be useful is in evaluating the effect of changes. So for example, if our reactor experienced some acidification and the pH dropped to 6.5, let's see what happens to the methane. So the methane content dropped from 68% in the biogas down to 62%. Well, what happens if we had a more concentrated waste stream of 150? And let's go back to a pH of 7.9. So now we see a methane content of around 65%. So it's a relatively flexible app, and there are a lot of different ways it can be used.